So now I'm going to tell you a little bit about how to get from electricity and magnetism to light waves. So you want to start with Maxwell's equations. In empty space with no charges or currents. So we want to make this as simple as possible. And if you write them with no charges or currents, they are even a little bit simpler than if you have charges around. And it's still enough to get a wave, to get light waves. So you'd start with Gauss's law. Gauss says the integral of E dot dA around a closed surface, normally you would say it equals the charge enclosed over epsilon naught, but I said no charges, so it's equal to 0. All right. And then let's see, there is the no monopoles law, which I like to sometimes call Cabrero's law, and it says that the integral around a closed surface of the B field equals 0. And that one really does equal 0 because there's no magnetic monopoles. Then let's see, there is Faraday's law. And Faraday says that the E dot ds around a loop equals the minus time derivative of the integral, oh, not around a closed surface, of the integral of B dot dA in the surface that is enclosed by that loop. So a changing magnetic flux basically creates an electric field. And then there is Amperes law. And Ampere said that the integral of B dot ds around a surface, around a loop, must equal mu naught I, the current going through the surface enclosed by the loop, but I said no currents. So in this case, we're going to say that one's equal to 0. Okay? So there's a simplified version of Maxwell's equations. Now you may wonder, why are they called Maxwell's equations? Gauss, Faraday, Ampere, nobody yet. What did he do? Well, he did a lot of things. So Maxwell came along a little bit after all these great guys. So he was sort of more middle of the 19th century. This stuff was figured out 18th century, early 19th century. He was more in the middle. And he came along and a lot of this was done. And he was very smart, very brilliant student. Everybody knew he was a genius. A little bit awkward when his parents sent him off to a fancy boarding school. He was a little bit teased because his dad liked to make him his own clothes. Right? So he would go to school in homemade clothes. And when I was 15, my mom made me a pair of jams, and I'm still trying to recover from that. So I kind of understand where he was coming from. So he did very well in school, became a physicist, became a professor. What is he going to work on? He says he really wanted to try to unify all the electromagnetism out there, right? Because it hadn't been unified yet, right? This is what we have now. So, and everybody said, oh, you'd never, why would you do that? Everybody's tried to do that. And one thing that helped him, though, is he got a copy of this guy's book, Michael Faraday, the greatest scientist that ever lived. Was a very good experimentalist, was really good at figuring out the exact experiment to do to understand what's happening in the world. Right? He invented the concept of the field, actually, but he didn't really know any math. Right? So Faraday was not raised wealthy and educated, so he couldn't really do all the math, but he could do the brilliant experiments, and he wrote them all down in great detail in this giant book, Experimental Researches in Electricity. So Maxwell got a hold of that. Right? So suddenly you have this brilliant genius holding essentially all the experiments done for him, described in painstaking detail by Michael Faraday. So those two things together let him do and see a lot. One thing he did is he fixed this one. You'll notice they're not symmetric. These two things equal 0 that look similar. These two things, this one equals 0, this one doesn't. That's because this one is missing a term. Right? So Maxwell showed that in addition to having a B field circulating a loop due to actual current going through it, you can have something called displacement current, which is really just a changing E field. So mu naught epsilon naught d dt integral of E dot dA. And now they look much more symmetric, and now it's called the Ampere-Maxwell equation once we fix it. So that's one thing he did, is he sort of fixed Ampere's law, and he brought them all together and showed that this set of equations sort of tells you everything about the electromagnetic field. It's not all these different parts coming together. He really put it all together. Although he didn't actually do these 4 equations. His original paper, I think it's 20 equations, because it was in some god-awful format that we don't want to think about, some other mathematical notation. But now in modern times, we think of it as these 4 equations. But even that probably isn't enough to get you your name on 4 equations and as the king of classical electromagnetism. The other thing he did is you can combine these to get 2 wave equations. And really to do it, you need to have them in what's called differential form, which you may have heard of. You can also write these in this sort of, using this sort of field theory differentials, this del operator. And if you write them that way, then it's not so hard to show how you manipulate them and get a wave equation. That's the thing, one of the things we're not going to do because this is trying to get to optics. But if you wanted to go back to 102X, the archived 102X class, it's all done there in learning sequence 10. But if you do that, you can show, I'll give you a little differential form, del squared E equals mu naught epsilon naught d2E dt2. So you find that to be the case for the electric field, and it's exactly the same for the magnetic field. Del squared B is mu naught epsilon naught d2B dt2. So if we accept that this is a field derivative, this is the same as saying d dx in 3-dimensional fields, we recognize this as wave equation, right? Back on the string, it was F equals ma. Now it's spatial derivative of E, some constants of the universe, and then time derivative of E. So Maxwell did that, and he said, that's interesting. He said, well, how fast would this wave go? Well, this wave would go, we know it's 1 over that squared. We know that this wave, whatever this is a square root of 1 over mu naught epsilon naught. And he thought, I wonder if anybody's seen a wave like that before. So in his head, he thinks, well, mu naught's about this and epsilon naught's about that. Those are known constants of the universe, the permittivity of free space, the permeability of free space. They had been measured at the time. And he realized this is a really fast wave. Like the speed of this thing is sort of on the order of 10 to the 8 meters per second. And he's like, what wave goes 10 to the 8 meters per second? And he realized it was light. Right? He realized that light is really an oscillation of the electromagnetic field. And that's really not something that people were thinking about. Okay? And the story I read is that he was on vacation when he discovered this, and he didn't have his books, and there was no Wikipedia, and there was no cell phones, and he couldn't get the exact values of mu naught epsilon naught and C to check it. He had to wait till he got home. Gets home, checks it, the rest is history, and he showed that light itself is just an oscillation of the electromagnetic field. And that's why we call it Maxwell's equations.